All right, so we are going to get started today by working with regressions. We're really just going to work with linear regressions, but it should give you enough of an overview to kind of have a sense of how working with regressions works in R. By the end of this tutorial, you will be able to create a model, predict new values using that model, and compare two different models to see which one is better. All right, so we are going to get started by installing the Broom package. This is going to help us clean things up as we go, so we'll go ahead and install Broom. We need three libraries. We need the tidyverse, and we need the lubridate. I actually don't know if we need lubridate, but one of our data sets might actually come from lubridate. And the Broom package. All right, so I'm going to highlight all three of those, run those, and they should all load in without a problem. All right, so we're first going to work with the trees data set. This is a data set that measures the height, the girth or diameter, and the volume of timber that comes from black cherry trees. More information about this data set is available in the documentation, which you can find by typing $trees. And it'll give you a little bit more information here, including links of where this data set came from. All right, so we are going to load the data set in. I'm going to say data, trees, and then we just want to take a look at it, see what this data set looks like. So I'll run those two. And we see that we have some decimals here. We have some point values. There's 31 observations, so there's 31 records, and only 3 variables. It's really just girth, height, and volume, with no other information about the trees. All right, so the first thing we want to do is see how this looks. We're going to be interested in the height and the girth measurements. With the hypothetical situation that we want to know how much volume we're going to get out of this tree. And it is much easier to measure how wide a tree is as opposed to how tall a tree is. All of these measurements were taken at about 4'6" off of the ground, which is a completely reasonable height for most adults to reach. It's a whole lot easier to measure that than really to measure the height. So we're going to assume that we want to figure out the height based on the girth or based on the diameter of the tree. So like I said, we'll start with a visualization. We'll type ggplot and we'll pass it the trees data set. Our aesthetic is going to be x equals trees, and we want the girth. So that's our independent variable, and our dependent variable we want to be the height. Okay, and we're going to make a scatter plot, so let's use geom_point here, and we'll add a title just for to be appropriate, to make sure that we're telling people what our plot is about, and our title will be tree height by girth. This is overall quite difficult to read, so I'm going to break it here so that we get it there on 2 lines. All right, go ahead and run that, and we get a scatter plot, and we have all of our trees here. All right, and we have the width of each tree ranging from 8 inches to about 21 inches, it looks like, and the height of each tree ranging from about 62 feet up to about 87 feet, give or take. So we have the height and diameter of each of our trees. So we'd like to see the line of best fit in this plot. So I'm going to call pretty much the same plot. Go ggplot trees, and my aesthetic will be x equals trees, $girth, and y equals trees, $height. And then I will add to that a point variable to make my scatter plot. And then I'm going to add a stat smooth. And what I get with a stat smooth is a line of best fit. And I'm going to tell it the method, and I want this method to be linear. I want it to make a linear model. And the standard error, I'm going to say false. We're going to talk more about standard error in a minute, but for the time being, I want to set that to false. And I'll keep my labels with my title equal to tree height by girth. Okay, go ahead and run it. And this should give us a line here, and this is really our line of best fit. And as we discussed in class, what this is doing is minimizing the sum of the squares. So the distance between this point and the line, and between this point and the line, and every other point and the line here, that is minimized in order to create this line of best fit. This is a method that finds the one and only line that is going to minimize all of the error between every single data point and the line that we draw. All right, so if it is really bothering you that we have one measurement in inches and one measurement in feet, you are welcome to change that. The details of how to do that are in the notes, but we're going to pass that now. All right, so we have this line here, and that's great, but it'd be way more useful if we can actually make a linear model that we could then transport around and do operations on. So we're going to actually call linear model. We're going to call this LM trees, and I'm just going to call LM in height by girth. And then my data is equal to trees. Now a quick word of warning here. You'll notice that most of the time when we write out our variables, we write out our x and then our y, or our independent and then our dependent. When we're making a linear model, we actually put our dependent and our independent because I want to predict the height based on the girth from the trees data set. And it's really important here that you use just plain height and plain girth rather than trees $height and trees $girth, because as you'll see, our variable names have to match identically for a later function. So using this dependent variable by independent variable comma data, as opposed to specifying the data with the variables, is very, very important. All right, so I have created a linear model, and then I'm going to call my linear model. And what you see here is that the call returns my formula. So my formula is height as a function of girth from the trees data set. And my coefficients, it very helpfully reminds you here, it tells you your intercept is 62 feet, and the girth is 1.054 times the girth makes the height. So what this is telling us is that for every 1 inch of diameter, we get about 1.054 feet of height added on for trees that are at least 62 feet tall. So it's saying that this doesn't really apply well to things that are too much under that. So it's not really going to work for a 5-foot tree or something like that. But once you get into a full mature tree, for every inch of diameter, you get another little more than a foot taller. Right? So as you see, simply calling our linear model doesn't actually tell us that much. We get a lot more information if we call summary on our linear model. So we're going to call summary LM trees, and you see here that we get a lot more information. So we get the same call telling us what our formula was. We get the distribution of the residuals, which will make more sense in a minute. We get our coefficients, and we get a little bit more information about our coefficients, such as the standard error. We don't worry about this. We get the residual standard error, so how much the overall standard error is, and the multiple r squared, which, as we discussed in class, is a measure of how closely this model fits this data. All right. So we will come back to that in a minute, but in the meantime, we want to make a couple other calls. One more call we can make is just to call the coefficients. Maybe I don't need all that information and I just want to see what my coefficients are. I can call coefficient LM trees, and then that gives me just the intercept and the slope. Okay, so that's all great, and that tells us a lot of information about our model, but what if we wanted to look at what our fitted values were? So what all of the points along here would be. So here I can call the fitted values function. So I'm going to call it fitted trees, and I'm going to assign it to fitted values, and I'm going to pass it the LM trees model. And what this is going to return is what the model predicted for each data point, as opposed to what was actually measured. So I'll call fitted trees, run that, and we see here at every inch of girth, so at 1 inch, 2 inch, 3 inch, we see what the model predicted for the height. So for all 31 data points in our set, we have what the model would have predicted for the height there, right? Which is kind of useful. These are also ordered in a ascending pattern. So you can look into here and, get a little bit more information about what the output of your model would be. Right? The other thing that can be really useful to us is looking at just the residuals. So how much was my model off from what was actually measured? So I'm going to set a variable residual trees. I'm going to assign it to residuals, and I'll pass the LM trees model. And then I'll call my residual trees. And what we find here, rather than what the fitted values are, we find how much each value differs from what was expected. So how much the measured value differs from what was predicted by this line. This allows us to see where our model was really, really far off. We see down here we got -12 for residual. We have 9, a couple of 9s over here. So this tells us not what was measured, but what the error was or what the noise was. Okay. It's really easy when you only have 31 data points, but if you have far more than 31 data points, let's say 3,100 or 31,000, you would need to look at those a little bit more strategically. And you might want to investigate some of these outliers a little bit more. One way to do that would be to rejoin the LM calculations with the original data points from the original data frame. This is where the Broom package comes in. So I'm going to call LM matrix trees, and I'm going to assign that to Broom and augment. So augment will allow us to take the original data set and our linear model. Right? And I run that, and I want to see what the head of the LM matrix trees looks like. All right. What we see here is the height and girth from our original model. We see the fitted value, the standard error of the fitted value, the residuals, the y-hat score, the sigma, the Cook standard deviation, and the standard residuals. Don't worry too much about these for the time being. What we're going to focus on the most is the fitted and the residuals. All right? So this has joined our original data set with the linear model and what would be predicted by the model that was fit to this data. Okay, So this becomes really useful when you want to see what has the biggest residual. So I'm going to call my LM matrix trees, which is this joined up data set that I have. I'm going to filter it by arrange descending dot resid, right? And then I will pass that over just so that I look at the head. I'll run that, and it looks like we have 9.95, 9.58. That's great. But when I was looking at the residuals before, I had a negative 12, and that's actually a larger amount off of what was predicted than 9.95. So in that case, I actually need to look at the absolute value. So I'm going to make a new variable, and I'm going to call it LM matrix trees dot resid, and then I'm going to give it the suffix ABS for absolute value. And I'll pass it to ABS of LM matrix trees $sign.resid. And I'm going to run that, and then I'm going to do the exact same thing. So I'm just going to copy this code here, and I'm going to paste it here, and I'm going to add underscore ABS. And I'll run that, and here we get what we were expecting. We get this negative 12.6 is the data point with the biggest difference. It has the biggest residual, right? So our prediction was the furthest off from our calculated value. Now, it's really important to identify this value because this may be an outlier. If we did have more information about this data set, we'd probably want to look more deeply into this variable. We'd want to take a minute to look and see, like, maybe this was a cultivated tree, or maybe this was a tree that came from a different region, or something like that. If any of that was the case, and we had good reason to believe that this was a very different tree, let's say maybe this was a tree that was in someone's yard and they were giving it fertilizer every day, or this was a tree that was grown inside, which is why it's so much shorter based on its diameter, right? So if we find out that all of the other trees in our data set were grown outside, except for this one, which was grown inside, well then we would have an argument for throwing away this data point. But without that information, we really can't. So let's see if we can get any more information about this tree. So I'm going to go back to my original data frame, and then the trees data frame, and I'm going to filter it by the girth equal to 13.8. So I've noticed here that the girth is something that I can call because that's also in my original data frame. So I'm going to go ahead and find this data point. And I run that, and I find that, as I already knew, there's no more variables in this data set that's going to tell me any more about this tree. So based on what we know, we're going to have to keep it. All right, so we're going to move on, and we're going to try to make a prediction. So we have this great linear model, and now let's say we are walking in the woods and we stumble upon another black cherry tree, and it's 19 inches in diameter, and we want to know how tall it is. So we're going to put our linear model into action for its predictive features. All right, so I'm going to make a new trees data frame, and this new trees data frame is going to hold all of the measurements that I take of new trees. But I went on a short walk. It's only one tree. So I'm going to call data frame, and I'm going to pass girth, and my girth is going to be equal to 19.0. Right? So I've given a new data frame that only has one data point in it. We could have a whole list of data points in it. It could be 19 and then 17.2 and 13 or whatever we found on our walk in the woods. What's really important here, though, is that we have a column, we have a variable in our data frame that has the exact same name as what we built our linear model with. So we have to make sure that this girth matches and that this girth matches. Otherwise, R won't be able to match them up for us. Okay. So I'm going to store my new trees data frame. And now I'm going to predict. I'm going to call predict lm_trees. And my new data is going to be my new trees. And I will go ahead and run that. And what I see here is that for that one data point, the first data point, I have 82.064. So our model has predicted that our new tree is going to be 82.06 feet tall. Okay, cool. That's great. But it would be a little bit more useful if I could join this to a data frame. So I'm going to call my tree, and I'm going to assign that to the augment function from the broom package. And I'm going to pass lm trees and new data equals new trees. So I'm going to join together my lm trees and my new trees all into my trees data frame. Okay. I'll call my tree, and we see that we have the girth of this tree, the fitted value, and the standard error of the fit, which is enough to put it on a plot. All right, so we are going to add this new predicted value and represent it on the same plot with our other values. So I'm going to call ggplot, and I'm going to pass data equals trees. On our aesthetic, x will be the girth, y will be the height, and then I'm going to add to that a point variable, and I'll add to that a stat smooth variable, and the method is lm, and we'll add to that another geom point, and this geom point is going to come from the mytree dataset. So this one is the new value that we're putting in. Our aesthetic is going to be y equals dot fitted, because this is not a measured data point. This is not a measured variable, but rather a fitted variable. I'm going to specify the size equal to 3 and the color to be red so that we can see it. Okay. And I'm going to add to that some labels, and it's going to be tree height by girth. All right. And go ahead and run it. And there is a problem. I have a typo. You probably already caught it. And there's another typo. Lab is labs. There we go. All right. So here is our new data point. And you see that because it was a fitted value, it is directly on the line. So the fitted value is not the measured, it's the predicted. So placed it directly on the line. All right. Excellent. So now we know how to use our model to predict new values. And let's take a look and see how well our model performed compared to the null model. So if you remember from the lecture, the null model is just the mean of the measured values, the mean of the heights. So we're going to make a null model with the height is equal to, or the height by 1. And our data is equal to trees. And what we're doing here is we're just setting a constant so that our height can be held in reference to it. And our tree null, I'll go ahead and call that. And we get our intercept is 76. Now, if we wanted to verify if that was true, we could also call the mean on the tree's height column, right? And we get 76 as well. So we see that the height by a constant will give us 76, and the mean of our tree's height will also give us 76. So it's really just the average of all of the height values, right? So if we knew nothing about the tree, if we didn't know its diameter, we just knew it was an adult tree, then we would say, it's probably 76 feet tall, because we'd have no other information to work with. Okay? So let's go ahead and plot that and see how that looks. And we'll call ggplot, and data is equal to trees, the aesthetic, x equals the girth, y equals the height. And I'm going to add to that geom point in order to get our points on. And I'm going to say geom h-line. And we want to say that the y-intercept of our h-line is equal to 76, that calculated value from before. And finally, we will add to that the labs. So we can give a title, and our title will be tree height and with null model. We'll run that. And there is a, I forgot to put my quotes. So now we'll run that. And what we see is this horizontal line that goes directly across our data set. And this would be our null model. And we can go ahead and add to our null model. We can go ahead and add to our null model the stat smooth call in order to get our linear model on there also. Right, so our method is going to be lm, and we'll add that to what we already have. And we see here that they cross, but for every data point here, the linear model is much closer than the null model would be for the vast majority of the points. All right. Last thing that we want to take a look at is the standard error. So I'm going to make another plot here. I'm just going to copy this, but I'm going to get rid of this H line. And I'll run this. Okay. So the last thing we want to look at here is the standard error. So the standard error is what's shaded here in green or in gray. And what the standard error represents is how much outside of this line is accounted for by the model. So when we were calculating the residuals and discussing the fact that it's normally, the noise is normally distributed, this is the amount of noise that is calculated by our regression line. So anything outside of this is noise that is not calculated by our regression, but everything inside of it is noise that we would expect per this model. All right, so the very last thing we want to do is assess to some extent how good our model is. So we're going to call summary again on our LM trees model. And we're going to take a look here at our multiple R squared. And we see that our multiple R squared for the LM trees model is about 0.27. Quite honestly, it's not that good. That's not a very well fit model, which is something that we also see here, that a lot of these data points, what looks like almost half, are not captured by this particular model. So we may want to reconsider how well this model fits our data, or how much we should really trust this model when trying to predict the height of trees. All right, so we are going to do one last thing with this trees data set. So we've looked at how we would make a model when we've already decided what variables to work with. But what if we don't really know which variables are going to be the most correlated with each other, or what variables we should inspect? So we are going to install the ggalley package. And it's ggalley. Run that. Because I forgot to install it earlier, and yes, I did mean ggalley. So it is 2 capitals, not lowercase. And then we'll go ahead and load our package, the ggalley. Run that. And we are going to call ggpairs. And what this is going to do, it's going to compare every variable that you tell it to. So ggpairs, data equals trees, and columns, I'm going to say do it on all of the columns that I have, which is columns 1 to 3. So if you had like 15 variables, you might do columns 1 to 15, or something like that. Okay, so I go ahead and this will finish loading. There we go. What we see here is each variable. We have girth and girth, height and height, volume and volume. And this gives us a scatter plot of each of these 2 variables plotted against each other. And this gives us the correlation coefficient. And just looking at these 3 variables, so we looked at height and girth, which the correlation is 0.592, right? Which is very low. It's the lowest of the 3. So what this does is allows us to see the variables that are most strongly correlated with each other. Again, correlation doesn't mean causation, so like girth does not create volume, even though it's a driving factor, particularly in cases like height, volume, and girth. But running this kind of exploratory data analysis will help you hone in on what variables you want to pinpoint. All right, so that's it for our introduction to regression. And now you'll go ahead and do a assignment on your own. So that's it for the introduction to regression in R. On your own, what I'd like you to work on is using the Longley dataset, create linear models for how 2 different variables predict employment rates. So as you're doing this, remember that the dependent variable comes first when building a linear model. And finally, I want you to identify which model is better able to predict the number of people who are employed. Okay. So go ahead and play around with the Longley dataset. The way that you call it is going to be like this, data Longley. And you can get more information about the Longley dataset by typing $Longley. And there's all of the variables are here. All right. So go ahead and finish this. And you can go ahead and submit your code with like 1 comment at the end of which variable you think is most predictive of employment rates, which one turned out to be the better variable. So this code that you write here, it would be the perfect thing to submit. All right. If you have any questions, let me know and have fun. All right, take care.